In this question, we're given that there is a current balance and there is a diagram. Let's take a look. Now in this diagram, there is a pivot and that's supposed to be a pivot. Show this a bit longer. A pivot, and then there is a wire. Okay, this is pivot. There is a wire that goes this way. That's okay, and we're given that there's a current that goes through this wire. So current going through this wire sort of goes around and come out here again, and that's the, let's see, the length of this side is 0.093 meter, and this side is 0.23 meter. Okay, 0.23 is from there, from the pivot to this end. Okay, and we are also given that there is a magnetic field of 3.6 times 10 to the power of -2 Tesla, and that there is so that's our magnetic field, and that there is a turning moment on this, just call it moments, of 7.4 times 10 to the, let me write this out more carefully, 7.4 times 10 to the power of -3 Newton meter. The question is, what is the current? Now, if you are familiar with a current balance already, then you would know that the force for the moment would act only on this arm, or on this part of the wire. Actually, the magnetic field spreads out everywhere, so there would be forces, there might be forces on the other arms as well. But that for current balance, we are most likely mainly interested in forces, or it is most likely designed so that the forces are mainly on this side, and if the forces are mainly on this side, then we would be looking at, say, thinking about the formula relating the magnetic field to the force, and that would be F equals to B I L. Alright, and once we know that, we would be able to calculate the answer quickly. And of course, if we are in an exam and we are in a hurry all the time, that's what we'll just go ahead and do that. So what I'm going to do is I'm going to just go through this quickly, and I'll come back to explain a little bit more about a few small but I think important points about the magnetic field and the force itself. Right, so let's just press on from what I've just said. Okay, so let's say we are in a hurry and we have straight away spotted this connection. Okay, because moment is force times distance, perpendicular distance from pivot. So that must be connected to the moment. Okay, and we're given a magnetic field, so force, force, magnetic field, so F equals to BIL seems to be the obvious formula to use. Okay, so the next step would be to relate this formula to all of these numbers that we've been given. Okay, so for the moment, let me call, to make things easier, let me give this some name or some symbols. Let me call this capital M. Let me call this length. Oh, that would be my L. Okay, so that's my L. Let me call this distance D. Okay, so and that's B, and I is what I want to find. So how would I use this formula? Okay, let's see. The moment here is related to the force and the distance by moment is equal to force times distance. The force here times the distance from the pivots. Okay. So let's see. How do we connect them? Right, we need to put this in terms of numbers that we know. So therefore the force here would be moment divided by distance. Force divide both sides by D, M over D. And we know M, we know D. So we can use this here. So force is M over D. B we know. I don't know, that's the question. L, we know. B, I, L. Okay, so we want to solve for I. So let me move BL to the other side. Divide both sides by BL. So therefore, I is equal to M over D BL. M over D BL. That seems simple enough. So let's try that. M 7.4 10 to the minus 7. 7.4 times 10 to the minus 3. Divide by D, which is 0.23 times B, 3.6 10 to the minus 2. 3.6 10 to the minus 2, and L 0.093. And we are ready to use our calculator. And the answer is 9.610 ampere. So that's the answer. And that's done, and we can put in the answer in the exam and go to the next question. But for this video, let me come back to this a little bit, this issue about the field and the force. Let's take a look at this. Actually, when I first read this question, even though I knew about the current, what the current balance is, I was a little bit unsure of where exactly the force is, because I wasn't sure which direction the magnetic field is. You know the direction between force and magnetic field is related by Fleming's left-hand law. But I wasn't exactly sure where the field is and where the force is, for the simple reason that there are many ways to draw a current balance. There are all sorts of shapes and sizes you can imagine, and for this particular arrangement, I wasn't actually used to this particular arrangement before this, and so in order to try and understand what's going on, I thought a little bit about the possible directions of the magnetic field. So let's see. Of course, if we can, just go through it quickly, like I said just now, and once we start talking about the moment, it becomes pretty obvious that's the simplest way we can do it is to just take a force on this side times this distance for the moment. So therefore the force must be on this side. But let's just try and check this by thinking about the possible direction of the magnetic field and see whether it makes sense as well. So if you think about the possible direction of the magnetic field, it can really be in any directions. But what we could do is we could think about some possible directions, okay, or some directions that might be simple that might relate to this picture in a simple way, and see if it makes any sense. So let's start by thinking about magnetic field which is in this direction and see whether it makes any sense. If B is in this direction, what does it mean about the force? Okay, if B is parallel in this direction, meaning it's not just along this line but spread all over, then it is parallel to this side, and therefore there's no force on this side. There can only be a force if the field is perpendicular to, or only if there's a component of the field perpendicular to the current. So therefore there's a force here and there's a force here. Right. But if you look at this, and that force must be perpendicular to both the current and the field. So that means it is either pointing out of this page or into the page. But if you look at the current is going to the right on the top side and to the left on the bottom side. So whatever force we have on these two sides must be in opposite directions. So they must cancel. Okay, since we're talking about uniform field and equal and opposite currents. So the forces must cancel. So therefore, if the field is in this direction, or if we think of the component of the field in this direction, it would have no effect. It would not give a moment, simply because the force here and here are equal and opposite, and they cancel. And that means that we can ignore any field or any component of field in these directions. So that's good. We have just eliminated that part. Now, what about the field going into the page? Let's say now I use crosses to represent this. So this would mean field going into this page. Okay. Now, if I have this field going into the page, let's see where are the forces. Field going in through the top wire. So again, because these two currents are in the opposite direction, okay, although there are forces on this wire and on this current, because this current is perpendicular to the field, the force on this must be opposite to the force on that. So without even trying to determine the exact direction with the Fleming's left-hand rule, once again we know that the force here and the force here must cancel, because they must be in opposite directions. So we can eliminate those two. Now if you look at this, right, okay, so there is a force here. Let's think what the direction of this force is. There's a current going down, and the field, going this way, downwards, and that's the magnetic field going into the page. Now if you take out our left hand and point our first finger in the direction of the field, that means into the page. Now middle finger in the direction of the current, that is down here. Find that the force acting on this current must be to the right. Okay, fine. But if it's pulling to the right, it's actually pulling along this side. That means pulling directly away from the pivot. So that's not going to give a turning effect. That's not going to give a turning moment. So again, any component or any field or component along this direction would not have a turning moment. So again, it's kind of not relevant to the question. Or maybe it's relevant, but it's not directly useful with the numbers given. So therefore, we are only left with one option. If the field is not going up or down, the field is not going into the page. Now the only component left is the component is a field direction, or the only direction left is a direction along this line. Okay. So if I have a magnetic field along this direction, this way, like V, this field would be parallel to these two sides. So there would be no force on these two sides. Okay. But it would be perpendicular to this side, and if we use the Fleming's left-hand rule, we would, or even without using the Fleming's left-hand rule, we would know that there should be a force on this side either out of the page or into the page. Okay, in either case, that would produce a turning effect or a turning moment about this pivot. Okay, so from here we can see that this is really the only field direction that matters. And although we can actually do the question without thinking about this, right? Knowing about this is always good. If you have time, of course, to give us a better understanding of the question.